Really? Okay. So, here's the formula, here's the equation that I ask you to write products for, balance those products, determine physical states, and then balance the equation. So, what I was saying is that carbonate is a polyatomic ion, and 3, this subscript 3, is part of that polyatomic ion. So that 3 there is going to automatically travel to the other side. Okay? There's the 3. Carbonate travel. The 3 in the carbonate travels because it's part of polyatomic ion. But this subscript 2 here does not automatically travel because it belongs to the sodium, and that's not a polyatomic ion. That's just an element. So we're only going to just put sodium here. Now we have to balance this formula. Calcium has a 2+ charge, carbonate a 2- charge. You find this on the periodic table with oxidation numbers. You find this on the common ions list. And since it's 2+ and 2-, we just need one of each. And so that is the formula for calcium carbonate. We don't need to put any subscripts or parentheses here. Okay, now, sodium is a metal. The only metal that tends to be anything other than a solid at atmospheric temperature and room temperature and pressure is mercury. So this must be a solid. Okay, mercury tends to be a liquid. We need to figure out the physical state for this compound. And this is where we're going to use the solubility rules here. Okay? So we're going to look through the solubility rules and see if we can find either the calcium or the carbonate listed here.
Yes, it's soluble.
Okay, so it says carbonates down here are what? Insoluble. They're not going to be soluble. They're not going to dissolve in water. Okay? Calcium's not listed anywhere. Okay? Well, but that's only when calcium is bonded with a sulfate. And this is not a sulfate, it's a carbonate. Right. Okay? So carbonates are insoluble. There's an exception when you have a carbonate bonded with a group 1 metal or with ammonium, and that's not either one of those. So if this is a carbonate and there's not an exception, it must be insoluble, and when you're in a water environment, that means it's going to be a solid. Okay? Alright, now we're ready to balance the equation. That's what you did for homework. And we're going to list all the elements: sodium, carbon, oxygen, and calcium. We're going to make our sort of chart or grid. And then we're going to count all the elements on both sides. Oh, sorry guys. Hold me up. Here you go. So, we have how many sodiums? 2 on the left. How many carbons on the left? How many oxygens on the left? How many calciums on the left? Okay, on the right, how many sodiums do we have? How many carbons? How many oxygens? And how many calciums? Alright. Alright. So the only thing that's not balanced right now is that sodium. Right? So how do we fix the sodium so that it's balanced on both sides? In front. So you have a coefficient 2. You're going to change this over to a 2. You know, balancing is easy. The point of this was to have you practice with physical states. Okay? Alright. Now, physical states are going to be very important. And when we have a single replacement reaction like these we've been working with so far, this is a single replacement reaction because I've got an element by itself that can potentially replace an element that is in a compound. Okay? That's a single replacement reaction when I have one element that replaces some part of a compound. Does that make sense? One part, 2 parts. That carbonates a part by itself because the polyatomic ion, it tends to stay together. So the one part substance can kick out or displace some part of a 2-part substance. Does everybody see where I'm saying 2 parts? Where we get that from? Yes? That's called a single replacement reaction. Before this unit is over, you're going to have to be able to classify 6 different kinds or classifications of reactions. Okay? This is the first of those we talked about. This is a single replacement reaction. All right? Now, it's important to be able to get the physical states right in a single replacement reaction. It's even more important to get the physical states right in a double replacement reaction. Okay? Now, the way that we know that this reaction will even take place up here is that the element that's by itself is higher on the activity series than the element that's like it in a compound. Okay? And that's called the driving force. The driving force for a single replacement reaction is the element that's by itself has to be more active than the element in the compound that it is like. A metal being like a metal. Okay? The driving force in a single replacement reaction is when a metal that's by itself is higher on the activity series than the element it's like in a compound. The driving force in a single replacement reaction is when an element that's by itself is higher on the activity series than the element it's like in a compound. Okay? I see a few people writing it down. If I said it more than once, it's probably pretty important. Okay? Now, the driving force for a double replacement reaction is different. So to know whether you have a driving force, you have to identify what kind of chemical reaction it is. Single replacement reactions have a one-part compound and a two-part compound. Not all single replacement or potential single replacement reactions even occur. Some of them don't. If calcium wasn't higher than sodium, this reaction wouldn't happen, and you'd simply write NR like we did on the post-lab sheet. Does that make sense? Okay? That's the driving force for single replacement. For double replacement, there are three different driving forces. For double replacement reactions, there are three driving forces. One is formation of a solid product in an aqueous environment. Two, formation of water. Three, formation of a gas in an aqueous environment. Now, only two of these will be used in this class. Okay? You have to know that this is a driving force, but you won't be using any equations in this class where a gas is formed, at least where you have to figure out when there's a driving force or not. Okay? You do have to be able to use these two at the top. Formation of a solid, formation of water. Okay? So here's an example. All right, so this is going to be a double replacement reaction. In a double replacement reaction, you have two-part compounds. In a double replacement reaction, you have two-part compounds. Okay, we've got calcium is one part of this compound, and nitrate is the other part of this compound. Okay, here we've got sodium is one part, and sulfate is the other part. So calcium, in a double replacement reaction, the front part of the first compound joins up with the back of the second. The front part of the second compound joins up with the back part of the first. Front parts always stay front parts. In a double replacement reaction, the front part of the first compound joins up with the back part of the second. The front part of the second compound joins up with the back part of the first. Front parts always stay front parts. The front part of the first compound joins up with the back part of the second. The front part of the second compound joins up with the back part of the first. Front parts always stay front parts. Kind of like mixing and matching your clothes. You probably have certain bottoms and tops that you can mix around and still have a nice looking outfit. Girls know this better than guys do. Okay? Generally. Alright? We can look around the room right here and tell, can't we? Alright. I mean, I'm sure you've got mix and match clothes, don't you? Okay? But you don't put your shirt on your legs. Don't be silly. You don't put your pants over your head. Okay?
That's where your underwear goes.
Okay, don't be silly. We're giving you an illustration to help you understand. If you make too many jokes about it, the illustration loses its value. And then you are not as well equipped to do well when the test comes around, or quizzes, or homework. Okay? Front part goes with the back part. That means I want to take the calcium here, and I want to put it with the sulfate. Calcium goes with sulfate. And the front part stayed on the front. Okay? Then I'm going to put the front part of this compound with the back part of that one. And the front part stayed the front part. Okay? Now we have two formulas to balance. Not just one. We have two formulas to balance. We need to know the charge on the calcium. What is the charge on the calcium? Look it up, please. Everybody, look it up and tell me the charge on the calcium.
Calcium is 2 negative.
Wrong.
2 positive.
2 positive. Calcium is 2 positive. Everybody look up the charge on the sulfate. What's, 2 negative. So how many of each of these do I need to balance this formula? 1 and 1, right? Okay. Do the same thing for sodium nitrate now. Balance sodium nitrate. Because we don't know if we need more than one. The only time you put parentheses around something is when you need more than one. I'm sorry, I didn't put a 2 here. So there's 2 of these in this formula. I didn't put that down a while ago. And we don't know yet if we need 2 over here. The only time you put parentheses is when you have a polyatomic ion for which you need more than one. Okay? We don't know that yet. All right? So what's the charge on the sodium?
1 positive.
1 positive, or just positive. And what's the charge on the nitrate? What? Don't confuse the subscripts and the superscripts. No, 3 is a subscript. The charge is in the superscript position on the common ions list. That's a common mistake. Good to get it cleared up now. So what's the charge on the nitrate? Just negative. How many of each of those do I need? 1 and 1. 1 positive and 1 negative cancels out. 2 positive and 2 negative cancels out. That's all I need is 1 and 1. Now we know the physical states, because this reaction doesn't even happen unless I have the formation of a solid product or the formation of water. Do I have water over here? So we know the second one doesn't apply. We're going to look for the formation of a solid. So go through your solubility rules and find the physical states for these two compounds now. What are the physical states for these two compounds? What are the physical states? So what's the physical state for calcium sulfate? Huh? Okay, how do you figure that? Okay, well, this is called sulfate. Okay? You need to know that. Okay? If you don't know that, write it down on your paper, okay? Write it above it so you can remember what it is. Okay? You have it listed for you on your common ions list. Write it down so you can remember it, okay? Then look it up on the solubility rules. Okay? Well, here's sulfate. Sulfates are generally soluble, except, what are the exceptions? Calcium. So this is not going to be soluble. Most sulfates are soluble, but not calcium sulfate, because calcium is an exception. Most sulfates are soluble, but not calcium sulfate, or strontium sulfate, or barium sulfate, or mercury, lead, or silver sulfate. Okay, so this is not going to be aqueous. If it's not aqueous, it's going to be solid. Okay, what about sodium nitrate? Is it soluble or is it aqueous? I mean, solid or aqueous? You got to find either sodium or nitrate in the solubility rules and figure it out. It's soluble. Both group 1 salts, and that's a group 1 element right there. So this is a group 1 salt. Both group 1 salts and nitrates are soluble. So this is going to be aqueous. Okay? Alright. We have 3 driving forces. We're only worried about the first 2. Do we have a driving force? Did we form a solid? We formed a solid. We got a driving force. This reaction is going to occur, so we're... Huh? Yeah, this one right here, we're forming a solid. So if the driving force is there, the reaction takes place, and we're ready to balance the equation now. So balance this equation. Balance this equation. We practiced all of yesterday in the homework balancing equations. You should be able to balance equations now.